Alrighty, folks, welcome back. Hope you had a good break. Our next speaker is a passionate advocate and steward of the AI community, contributing both technical expertise and mentorship to her teams. She's now a software engineering lead at Infor, here to talk about semantic caching and retrieval augmented generation systems. Ms. Sravani Lingam.
Hi everyone, thanks for being here today. I'm Shravani, and today I'm going to talk about something very simple yet extremely powerful, especially when you're dealing with production AI systems. Over the last few years, many of the teams have done a great job in building rack systems. But when these systems move from demo to production, all the new issues show up. High latency, high cost, or the systems that do not scale well under the load. These are the exact challenges that we are going to tackle today. Let me start with something simple example now. Let's say you contact Amazon customer support and started asking something simple like, how do I reset my password? And now imagine 10 more customers asking exactly same thing but in different ways. One person asks, I forgot my password. Other person says, password help. And other person says, recover my account access. Different wording but clearly same intent. And surprisingly, most of the systems today consider all of these questions as a complete different and new questions and run the entire pipeline every time. Let's look at what exactly happened when a user submit a query to the system. The system takes the user query and convert it into embeddings, and then it search through the vector database and retrieve all the relevant documents, and then it pass all the context to LLM to generate a response, and finally the generated response is written to the user. And here is the most important part. For every question, the system runs the entire pipeline, which means even question was asked just few seconds ago, even the answer hasn't changed, still the system runs everything. There is no shortcut, no reuse, or no memory. The system has no way of saying, I have seen this question before. As now we have seen the full pipeline, let's look at where the time actually goes. If you see the breakdown, most of the time is coming from LLM generation. Embedding, retrieval, or vector search, they do take time, but those are negligible compared in front of the LLM generation. LLM generation, for every request, it almost takes 2 to 4 seconds. And in many cases, it accounts for most of 80 to 90% of the total latency. Now imagine this at scale. Almost 20 to 40% of the production queries are repetitive. So now we are essentially paying for the same reasoning again and again and again. Let's take a simple example. If your system handles almost 1 million queries in a day, and roughly if you consider 30% of them are repetitive, which means we are doing 300k expensive LLM calls, which means 300k times your system is spending for the same reasoning. That is exactly why this optimization matters so much. Even if we can avoid a fraction of those calls, we can unlock massive gains in terms of both speed as well as in the latency. So you might think, why not just use traditional caching? Traditional caching works very well when there is an exact word match. For example, reset password works very well because it is already in the cache, so it can deliver. So even if there is a tiny small change, this would break. For example, reset password with a space typo won't work. Forgot password is a complete different wording, so it won't work. How do I reset? Again, it's a complete different wording, it won't work. This is a huge limitation of traditional caching. It depends on the exact matches and it works very well for the structured systems, whereas human language is messy. We do introduce a lot of typos and use synonyms and ask the same thing in many different ways. So exact matching in this case doesn't work well with conversational AI systems. So now we have two problems at hand. First, recomputing everything is expensive. Second, traditional caching doesn't work well with AI's conversational AI systems. So clearly this is not a memory problem. If you see, the system has a recognition problem. The system is unable to recognize that two different questions mean the same intent. Like, what if the system can understand the meaning? What if the system could say this question is semantically similar to the question I have already seen before? This solves everything. That's where semantic caching comes in. Instead of matching text, now we match meaning. Match meaning. How can we do that? When we are trying to convert user query to embeddings, embeddings is basically a vector representation of meaning, which means a list of numbers that capture what the question is about. If we say two questions mean similar things, their embeddings lie close to each other in vector space. Then we can calculate cosine similarity. Cosine similarity gives us a score that tells us how aligned those meanings are. If high cosine similarity score, meaning two queries are more likely to say the same intent. If we go back to our earlier example, reset password, forgot password, recover account, both three of them land in same cluster because all three of them, meaning even though they look different, they convey the same intent. And if you see, the cosine similarity score of them are also higher. Whereas if you compare reset password with delete account, those two are complete different things. Even if you see, cosine similarity is lower, which means delete account lies in a different cluster compared to our previous clusters. So now we are no longer asking, have I seen this exact query before? Instead, we are asking, have I seen something semantically similar question before? At a high level, the system still works in the same way whenever user submits query. But here, if you observe, we have introduced one important architectural change, that is cache in front of the LLM call. So whenever user submit a query, before passing that request to LLM call, we first check in the cache whether we have seen something similar. If we have seen something similar, we can directly serve it from the cache. If not, we'll reach out to the LLM call. This one architectural decision changes everything because now LLM is no longer on the critical path for every request. Let's walk through the flow. Whenever users submit a query to the system, we convert the query to embedding, and now we compare those embeddings with the set of embeddings that we already have in the cache. If there is a strong match and if it exceeds the threshold that we set, then we directly serve it from the cache. If not, it's a LLM cache miss, which means we want to run, the system runs the entire pipeline like before. We call the LLM and the LLM generate a response, and now instead of just serving the response, now we store that response in the cache for future reuse. So over time, the system becomes faster because more similar queries are answered from the cache, not from the model. This is what makes semantic caching more powerful in the production systems. There are two key decisions that really define how this system works. One is cache first strategy, the one just we discussed before. We always check the cache before calling the LLM. This is the foundation of everything. If you skip, you will lose most of the benefit of it. The second one is similarity threshold. This is the most important knob in your system. This is what decides how strict or relaxed a cache can be when it is looking for the matches. And that is where even the trade-off begins. If the threshold is too low, which is good, you get more catch hits, but at the same time, we may end up having wrong matches. If it is too strict, you avoid mistakes, but at the same time, we miss too many good reuse opportunities. So this is really a trade-off between efficiency and correctness. And the key is you do not have to guess it. You can tune it using real queries, outcomes, and real evaluations. So far, we have looked at the semantic caching inside a single system. This slide shows what it looks like in a distributed production environment. If you see, load balancer routes incoming requests to one of the RAG instances. If you see, the RAG instances are operating independently, which means the system can scale horizontally by adding new instances if needed. All of those instances are connected to one centralized semantic cache. Centralized semantic cache store embeddings and previously generated response so the whole system can reuse it instead of one single instance. Let's walk through a flow. Whenever a new request comes in, one instance receives it, converts into embedding and compares and check the central semantic cache whether we have any similar question answered before. If there is any match and if it hits the threshold, it returns directly from the cache. If not, we'll reach out to LLM. LLM will generate a response, and whatever the response we get, we'll store it in semantic cache for future use. The biggest benefit is that one user solved query can help future users across the whole system, not just one instant. So if a user in New York asks the question first, and a user in London can benefit from the cache result. This is what makes shared semantic caching more powerful in production. Let's compare the two side by side. Without cache, every repeated request go to the LLM model, which means higher cost, higher latency, and repeated use. With semantic caching, most of the cache hits are delivered from the cache. So there will be lower cost, lower latency, and reuse of answers. The difference is simple. One system recomputes everything and other system remembers it. At a small scale, this feels like an optimization, whereas at large scale, this becomes an operationally essential step because of few reasons. First, it helps absorb traffic spikes. The cache takes repeated requests out of the hard path so that LLM doesn't have to serve every question, which means it reduces infrastructure load. You need fewer models and you need fewer resources to serve the same traffic. Third, it improves stability. Now the cache becomes a buffer between your users and your most expensive component. Till now, semantic cache looks great, but it of course comes with a lot of challenges. One is, a few of the challenges mentioned is wrong matches, stale data, cold start, or privacy risk. Let's explore each one of them along with the best practices to follow. Cold start problem. When the system first goes live, cache will be empty, which means every request will be a cache miss. So here for every request we are running the entire pipeline. So which means higher cost and higher latency. In order to reduce it, one solution is cache warming. Cache warming is basically we will pre-populate the cache with common queries from either it can be from historical logs or domain knowledge. So instead of starting from zero, we start with useful coverage on the queries that most user asks for. Stale data. A cached answer may look correct in the beginning when we stored it, but later what if the source data changes? All the cached answers become invalidated. We can't serve the wrong answers to the users. So what can we do? In this step, the first one we can do is introduce time to live. Time to live for each question, for each use case, it can be different. For fast changing data, it can be few minutes. Whereas for general assistant purpose, it can be for few hours. And for the stable documentation questions, we can store it for a day or two or more than that. So it depends on what use case we are dealing with. And when we know the source data is changed, we can either invalidate or refresh all the affected entries. So we can serve the correct results to the users. For wrong matches, we tune the similarity threshold carefully. We have already discussed this before. Instead of coming with random guesses, so we tune thresholds based on real queries, real outcomes, and real evaluations. And the next issue is privacy. In multi-tenant system, the cache must enforce strict isolation so that one user's sensitive information is not leaked to other user. So this means we can introduce tenant-aware keys, namespaces, and access controls. Along with all of this, we need careful monitoring and continuous feedback loops. We can track hit rate, miss rate, a latency for hits versus misses, and false positive rates. This way, we can make the system efficient. The key takeaways, like don't recompute solve problems. If there is any semantically served queries has already been answered, serve those results from the caches. So because as every redundant LLM call is waste of computing, wasted latency, and wasted money. Second, cache meaning not text, because exact matches in conversational systems is rare. So and we use natural language which can be messy. So if you catch meaning instead of not text, so we can reuse most of the answers. And last, semantic caching is not optional. It's not nice to have. It's a required layer for all the production AI systems. Yeah, that's it. Thank you.
That was very time efficient, so we have plenty of time for questions.
Some of the orchestration frameworks like LangChain, does it have semantic caching built into it, or do you have to build it from scratch?
Semantic caching, like, yeah, you have to build, like, because each use case is completely different, right? So it depends on use cases, what you want to store in the semantic caching. Any, like, you can use Redis or any, like, whatever the databases supports vector, like embeddings, you can store it there, like using PG vector in Postgres, or so it depends on from use case to use case. Yes.
I have a question on the threshold tuning. So logically, how I look at the problem is that when you first ask the question to the LLM before you cache it, Similarity is going to say, oh, this is an 80% match, okay? And then that gets cached. The next question might be 80% away from the original question. So now the answer's only 60% matching the answer. Do you follow what I'm saying?
Yeah.
So how do you manage that? What stats can you capture to say, hey, these are situations where I'm getting more wrong answers because the difference between those two matches has made the answer worse?
Yes, that is basically you can come up with before pushing it to production, you can come up with set of questions and set of answers and see what happens, like with your algorithm, what thresholds it is working well and what thresholds with the threshold value of, like, are there any more cache hits and we are not delivering any wrong information. So basically if you tune with the set of questions you have in mind, you can come up with the threshold.
And how do you assess whether that second answer was wrong or not? Do you do that semantically? Do you do that?
Yeah, it's semantically, because if for your use case, if you, like, after evaluating with the set of golden data set that you have, and if you come up like, okay, for my queries 0.7 works well because this is where I am not delivering most of the wrong information, and if I see the queries, these are like even I am using caching very well. So with that, like, that basically the semantic caching works with a like meaning as well, right? So you will tune based on the golden data set you have. If it works for this threshold, then you will go with that threshold. And it's like as I mentioned, it will be a continuous monitoring and feedback loops. Your data may change, so your golden data set changes every time. So offline you can check what threshold works for your case and you can go with that threshold value.
Thank you.
Yes.
Is there any concern about introducing that step of converting the query to the vector that may add more latency and the user may have to like wait longer to get their answer back, or it's not really?
No, it's not really, because like normally vectors, it will be like almost 512 bytes. So it will be easy to generate, like if you convert into, it's basically numerical representation which give us the meaning of the question, because it is, everything is in English, right? So you can't ask the system to find the meaning. So there should be a way to convert to a numerical vectors. So the numerical vectors is basically the vector representation, and now it is like there will be like almost like 1500 a dimensional space, which is 1500 bytes, so it will be very quick to compare. Yes.
Have you seen results get worse or perform worse over time with the prompts being cached?
Yeah, it's a good question. It depends on use case to use case. It was like, if you use the semantic caching in where answers change, like data changes very quickly. So at the time, as I mentioned, TTL or something, you have to change it for every minute. For every minute, like if you want to change the data for every minute, so instead of caching, you can directly serve without caching. So in that case, it will be a wrong example to use a semantic caching. But whereas for most of the systems, like as I mentioned, Amazon customer support or most of internal FAQs, in those kind of questions, almost everything are repeated queries. Almost every user asks similar kind of questions. In that in that semantic caching works very well, because you almost have most of the repeated queries. So instead of passing everything, if you store, you can just directly answer from the cache, which will be like which will take less than 5 milliseconds compared to the entire LLM generation.
Sorry, follow up. Are you able to capture the consumer or the user feedback? So whether or not they like the response that they got, are you incorporating that into the cache?
Like yes, normally, like as I answered to the previous question, one of the previous questions, which is basically when you come up with the golden data set, obviously we will take like continuous feedback as well, like whatever the user feedback we will input to the system. So make sure what thresholds are correct, what thresholds are not correct offline, so we can come up with the threshold tuning, as well as like where it is going wrong, where it is going correct. So it's a continuous monitoring.
So in this scenario, we're actually retrieving from cache without really persisting session. In some cases, the same person asking 2 questions in a row, the intelligence from the 2 questions in the session actually feeds back to more accuracy with the response coming back. So in the case of this one-shot question, having the retrieval coming from cache rather from the model, do you lose information? Do you lose accuracy in this case, because you're only getting half of the question out hitting the model?
Sorry, I didn't understand. Can you repeat it? Yeah.
I think I'm trying to solve the problem myself. So in a normal scenario, one question, let's assume it's one question, one answer. Right? So if one question hits cache, it never hits the model, right? But if I have 2 questions, and the second question depends on the answer coming from the model. All right, that's session knowledge that's stored in session. Do you lose any accuracy from the second response, given that the first response is coming from cache?
Yes, like if it is like, if first question is in the cache, so it will, like we'll save, like obviously like as we are fetching it from cache directly, we'll save like cost and latency there. The second question, we will check like whether we have it in the cache or not. Like if it is not in the cache, then it has to go through the entire pipeline.
Okay, so in this case, do you send the first question along with the second question, or just the first one?
Like if you say related to the context, like related to the context above, we will be like if it is related to the first question, then we will check what is in common in the cache and what is not. In the cache, we will be even storing all the relevant documents as well, right? Like regarding a RAG system. So relevant chunks, like whatever the relevant chunks it has, it will append, and it will, whatever we do not have in the cache, it will reach to LLM.
What sort of metrics have you studied for this? Have you actually run metrics to show that yes, this system is resulting in X faster speeds or more user satisfaction with the answers? What type of measurements have you made?
Yeah, cache hits, cache miss, and what is the latency for cache hits and what is the latency for cache miss. So these are the main important metrics, as well as how much of the percentage is hitting the cache. So if so, how much amount of cost or how many times we are calling the LLM is reduced.
So cost to the LLM, that's a key metric. It sounds like the speed from the end user too. I mean, have you looked at that specifically and the user satisfaction with that answer?
User satisfaction is through the feedback loops that we collect, if they give thumbs up or thumbs down to the message, and which we use for the even continuously monitoring and teaching our the entire pipeline.
Thank you.
Hey, you had some really good slides on the privacy pieces. I'm glad you touched on that. I was curious because you kind of have an inverse relationship on where your organizational boundaries are for your caching. How did you balance how much privacy versus how much global coverage you would have with your cache results?
Yes, for this especially, I think I have touched down here, so sorry. Yeah, as I mentioned, here, tenant aware keys, we will come up with tenant aware keys, namespaces and access control. So we will check what kind of tenant has this information, because if it is more of internal, if there is an internal user, we can provide more information. If it is not, we can provide less information. So this we can achieve through a tenant aware keys.
So does this get used on a multi-turn conversation, for example? Could a result get potentially cached if, say, the user input some sort of PII in there, it got cached as a result, or do you tend to generally just use your kind of golden set of responses only and not user-generated responses?
Whenever there is a sensitive information in it, we do not store it in the cache because it's a violation. If you have sensitive information, we remove the PIA data, then whatever the information we have, that we will be storing in the cache.
So you have PIA guardrails before they go to cache, basically.
Yes.
So you talked about the pre-warming of cache and the top 20%. So how long back do you go in logs? Is there 30 days back or through, or do you try to find that top 20% from all the?
Yeah, basically in cache warming, we will be storing because it's a complete new system. So we do not have any entries in the cache. So we will be storing as much of information we can, but especially if there are if there is lot more information, we can't store everything in there, right? So we can go with top 100 questions, what are questions that the user asking, and then that information we can store so that we can encounter almost 30 to 40% of the people asking same of this, so we can serve from the cache. If not, we can learn by running the entire pipeline, and if there is a new question, we can run the entire pipeline, and the result, if we do not have that in cache, we can store that in the cache.
You do realize over time that log of data can keep increasing.
Yes.
That will have to go.
Yes. So if it is increasing, we do have TTL, as I mentioned, we have time to live as well. So you can choose how many days that can be in the in the cache store. If not, we can remove it based on those TTLs. And TTLs can vary depending on the use case. So it can be for a few seconds, it can be for a few minutes, it can be for a few days as well.
Right, got it. Yeah. I was assuming 30 days.
I think we have time for one more. All right, another round of applause. Thank you so much.
Thank you.